Welcome to Hydration Lecture Series. My name is Stavros Kourouras. Welcome for all of you that you're here in the room, and also welcome all of the online viewers. It's my great pleasure today to have Dr. Robert Kenefick in our university and here with us. And he's going to be talking on the effect of dehydration on exercise performance. Dr. Kenefick, he's a famous researcher in the area of hydration and exercise performance. He's probably, if not the number one of the leading names and leading scientists in the area of hydration. And how does hydration affect exercise performance and also health and overall well-being? So without any further ado, thanks for coming in the University of Arkansas, and I look forward to your presentation.
Thank you. Thank you for having me. Thank you for that really kind and overblown introduction. Most of the things are not actually true, but that's okay. Before I start, I want to thank the university. I want to thank Dr. Kourouras and Dr. McDermott and Dr. Gano for inviting me down. Never been to Arkansas. It's beautiful. I hear you guys are into football. So I'm going to talk a little bit about my institute, just to kind of get you educated as to where I'm from and what I do. And then I'm going to talk about the presentation and what we're going to have. And as you can see here, as JT, right? JT was saying to me, right? That's close. So as JD was saying earlier, that map there on the bottom left is our institute. That's what we call the map of Texas. We're on a peninsula surrounded by water. It's an Army base. You can see that we're located about 10 miles due west of Fenway, Red Sox. If you guys are into baseball, we're about 12 miles north of Gillette Stadium, where the Patriots play. Maybe you heard of them, 7-0. Okay. Anyway, so a little bit more about our institute, because it's a unique place, and a lot of people don't have the opportunity to come and see it. And this is our institute itself. And this is our organization. So we're privileged to have 4 different divisions who work doing research for the Army. We have a biophysics and biomedical modeling division, and they're responsible for taking physiological data and creating models. So if any of you are good at math and looking for jobs, we'd like to talk to you. We use these models to predict things like fluid needs, what your heart rate might be, what your core temperature is. And this is important for mission planning, so that's one division that we have. We have a performance division. Their specific job is to do very applied research, looking at specifically military tasks, but they also do other things like bone health, and they do some cellular work. So I know you guys have a muscle physiology program. They do that work there also. We have a military nutrition division, and they're responsible for doing everything that the soldier eats. They do a lot of work with supplements. They do a lot of work in the field. So they're an interesting and pretty prolific group. And then there's the group I'm in, the Thermal Mountain and Medicine Division. And we do all things environment, which includes heat, cold, altitude, hydration, dehydration. And I've been there for about 10 years. Okay. Can I just hit the red thing to make this go away, or what's the deal here? Okay. We're a no-go here, Stav. I was joking with Stavros, texting him. Usually I have to find somebody at the airport. I have to find like a kid like you guys to work my phone or my computer. So this should not be surprising that. There we go. All right, a little bit about our facilities, because we have some world-class facilities I'd like to share with you. Our building itself, and you can see it here, is our building. Maybe you can't, but our building is has its own chambers inside of it. We have 4 chambers, and you can see this is actual pictures on the left side of the screen of us doing some research in our facilities. We also are next door to the Dorio Labs. This is a climactic facility. It has 2 of the largest chambers in the North America. And you can see on the right and left side, those are the actual chambers themselves. They're probably about as wide as this room and maybe twice or 3 times the length of this room. So we do physiology testing in there. You can see we have 2 large treadmills. We can put upwards of 5 people per treadmill, and we can test in mass, which is actually very convenient when we're doing things like heat acclimation. We have a cold pool, so we can do some cold immersion work and submerge individuals to varying levels of cold water or warm water. We do work in the field, so we have a lab on top of Pikes Peak. We've been there for the past few summers. We're going to be out there next summer doing work there. We've also done field studies. I've gotten to climb Mount Kilimanjaro doing a study all the way up the mountain. So we do get out into the field quite often. Back at our facility in Natick, Massachusetts, we have our normobaric hypoxia. So this is where the oxygen content of the air is changed, but the barometric pressure stays the same. And then we have a hypobaric chamber where we're actually able to change the pressure and simulate various altitudes. We have an animal model. We have a whole animal facility. So we have some folks who've created a heat stroke model, a rodent heat stroke model, one of the first one in the world. So we're able to study heat stroke by taking these animals and giving them a heat stroke and study what happens to them, because obviously we cannot do that to human beings. And our mission is to conduct biomedical research that's going to improve and sustain warfighter health. And we'd like to be known as the internationally recognized Joint Center of Excellence for warfighter health and performance. But that doesn't mean that we don't actually do work that benefits other people. Obviously, I'm here to talk to you guys today. We go out and we speak to lots of other groups. Many of you may have read our research, so we publish all or almost all of our research in scientific journals. So we do actually get out. It isn't just our main customer isn't just the Army. We do get information out to other sources. All right, so first I'm going to tell you what I'm going to tell you, and then I'm going to tell you, and then I'll tell you what I told you. So this is a brief outline. I want to talk briefly about some dehydration terminology, so we're all on the same page as what we're talking about as far as dehydration. I want to talk a little bit about what's constituting dehydration, the types of dehydration, and the differences. And this is important because people just believe that dehydration is a blanket statement, and that's not always the case. I'm going to focus today specifically on cardiovascular and thermoregulatory responses to dehydration. There are other responses, but we're just going to focus on that today. We're going to talk a little bit about how dehydration alters physiological performance. And then I want to talk about the real take home is, when does it matter, or does it matter? So, dehydration, is this a topic of controversy? Well, if you go ahead and look in the literature, this is from my former boss, Mike Saka, and it's a point-counterpoint with Tim Noakes, was in MedSci in 2007. And if you look at this, you can see in the literature, there are some ideas that are expressed here out in the literature. And one of the ideas that Dr. Noakes puts here is that these studies actually don't show that there are any changes in performance, that individuals actually can finish really long races, like ultra marathons of 100 miles long, be 10% dehydrated, and have no impact on their performance because they finished or they did really well at the race. So you have that out in the literature. Dehydration doesn't really impact performance, or really doesn't impact it that much. And then on the other side of the literature, you can find studies out there that say minimal dehydration has an effect. Very, very low levels impact lots of different things like cognition or physiological performance. And then there's people out there who say any level of dehydration is dangerous. It can increase your body temperature even at rest, and that could put you at risk for a heat illness. So is this an area of controversy? I would say it still is, even now. And we still get these questions as to whether or not it's actually important. So we get calls all the time. I might get a call from some commander who's planning a mission to do something. We get calls. I just got one from Men's Health. People call us all the time, and they say, hey, how much fluid do I need to drink? Like this guy's drinking right now. How much do you need to drink? That's the question. You know, and this is what you're going to have in your careers. And you guys get out there, people are going to go, hey, I just need to know how many sit-ups to do. Just tell me, 20, 30, that's all I need to know. People say, how much do I need to drink? Just tell me, give me a number, and I'm fine. But the problem with that is it depends. And if you take nothing home from this lecture today, other than it depends, then that's really the take-home message. That's really what I want you to know, okay? And that should kind of be a preview for whether or not, or in what circumstances dehydration plays a role. So let's talk a little bit about body water, and let's talk a little bit about these terms that I've mentioned about dehydration. This is adapted from an article from Greenleaf, and I think if you guys are serious in this area, this is something that you should definitely read. And it talks about the state of hydration being a dynamic equilibrium. And you can see that sinusoidal wave there in the slide. And basically it's telling you that your body water fluctuates from day to day around 1% of your body weight. And this is a normal fluctuation. This happens every day. So when we talk about hydration states, well, I'm talking about dehydration, but when you look in the literature, you'll also see another term called hypohydration. You guys have probably seen that. And typically the terms are used interchangeably. Today I'm just going to talk about dehydration, but you guys know what I'm talking about. A lot of times dehydration is used as the verb, you dehydrate, and then when you're in the state of body water loss, you are hypohydrated. That's the real true definitions. But for what we're going to talk about today, it's dehydration is going to be the term that we use. And you can see, and this is an important point that I want to make, this sinusoidal wave can make it difficult to really establish when someone is euhydrated, normally hydrated, because your body water fluctuates. Let's talk a little bit about where this body water is, how we gain fluid, how we lose fluid. You can see here I'm starting with an individual to look at their total body water of somebody who's 70 kgs. And out of 70 kgs, about 45 liters of that is going to be total body water. What's important to remember is that individuals who may be more obese are probably going to have less total body water because they have less muscle mass, and people who have more muscle mass are going to have more total body water. Okay? That makes perfect sense. Where is all this fluid located? Well, you see the bulk of it is located in the intracellular fluid. About 67 or 70% of it is held intracellularly. The other parts of the fluid are held in interstitial spaces. That's the fluid surrounding your cells. It's about 25% of your total body water. And then about 8% or about 3 liters is held in the plasma. And you can see that there's exchange among all these fluid compartments using capillary exchange and osmotic forces. What's important for you guys to understand is that fluid balance is a measure of fluid intake versus fluid output. And when we talk about output, we're talking primarily about urine and sweat. But it's also important for you guys to remember that you guys are actually losing fluid right now. You have transcutaneous fluid loss out of your skin. You lose it in fecal matter. So there are other ways that we're losing fluid, but for our purposes today, we're really going to talk about the predominant fluid losses being sweating. So what are those signals for sweating? And you guys probably know this. This seems like it's complicated, but it's not. If we start here on the lower left-hand side, you can see that there are 2 major signals that are going to be driving your sweating. The first one is your body temperature, core body temperature. That's going to be reflective of your metabolic rate, or if you're exercising and creating heat, or you could be gaining heat from the environment. So that information is going to your hypothalamus. You're also getting information from the environment, from your skin temperatures, also being integrated at the hypothalamus. It's being compared to a set point temperature. And then your hypothalamus is going to give some information or responses back for you to maintain or keep you guys know what I want to say, equilibrium for your body temperature by either starting sweating and increasing vasodilation. So the predominant loss of fluid, at least in the scenario we're talking about today, is going to be exercise. Well, again, we go back to how much fluid do you need? And so this is Dr. Bronson Prickle, leading cactus scientist, who would recommend that you drink 8-ounce glasses of water a year, 0.2 ounces a day. Good recommendation. Depends. If you're a cactus, maybe. But how about humans? So this is a great slide that tells you pretty much nothing. It's like, okay, if I drink too much, I'm going to be overhydrated, and I'll have an increase in my body mass. And then if you look on the left side, if I drink too little, I'll have less body mass. I'll have the body weight loss. And I need to be in this Goldilocks zone, right in the middle, right? I need to be well hydrated, euhydrated for optimal hydration. But the question still remains, how much is that? Well, like I told you before, it depends. So one of the things it's going to depend on is the environmental temperature. As you can see, it's here on the x-axis, and centigrade and Fahrenheit on the x-axis above, and activity level. Okay, so you can see right here, if you're looking at the y-axis, how much fluid you're going to need. You might need as little as 2 liters if you're living in an area that's rather cool and you're not doing a lot of activity, as opposed to if you're very, very active in a 40-seat environment and you're highly active, you can see you can need as much as 12 liters. And so when we get called by somebody, and they'll say, hey, my guys are in garrison, how much do I need to give them? We'll say, well, anywhere between 2 and 12 liters. It depends on what they're doing. So let's talk a little bit more about activity. What else is driving your sweating rate? And one of the other factors that we take into consideration as physiologists is exercise intensity. If you look here, we're seeing sweat rate on your y-axis. You can see you might need as much as or as little as 1/4 of a liter of sweating to thermoregulate when you're in a cooler environment and you're running at a very slow speed. As opposed to if you're in a hotter environment, as we get up towards the top end of this graph, and you're going very, very fast. So exercise intensity is going to drive fluid loss because the higher your exercise intensity, the more heat you generate, and the more you're going to need to dissipate that heat from thermoregulatory sweating. So here's another factor. It depends. It depends on your environment, and it depends on your exercise intensity. What else drives sweating or plays a role in mediating sweating? Well, I've already said that intensity plays a role. Obviously, duration of the activity. How long is it going to go? Am I running for 15 minutes versus am I running for 5 hours? The environment, and we could do a whole talk just on environment itself. So that includes the temperature itself, the humidity, and clothing, which is a big deal for us in military. A lot of these guys are encapsulated or they're carrying heavy loads. That plays a role. And then, of course, there are individual differences, your body mass, your metabolic rate, genetics, fitness level, acclimatization, whether or not you're used to heat. And know that your sweating rate is highly individual. You guys all are going to sweat if I put you in the heat, but how much you sweat is going to be very individual. So it seems pretty easy when these guys call me up and say, how much should I drink? Well, it seems, if you want to maintain a normal hydration state, you take in as much as you're losing, right? You fluid in and fluid versus fluid out, you should be fine. But that's not always the case. And so why isn't it always the case? Let's talk a little bit about these types of dehydration. So when people become dehydrated, what is the state that they're in and how are they different? This is a distinction that's not often made, and I just want to put it out to you guys because I think it's important. We talk about, and for today's purposes, I'm talking about exercise thermoregulation via the evaporation of sweat, okay? And so that leads to a state of what we call hypertonic hypovolemia. And I'm going to talk to you a little bit more about that in a second. But you also know that when you have vomiting and diarrhea, or if you're exposed to cold, or you go to altitude, you are also going to lose fluid through diuresis. You're going to become dehydrated. That dehydration is not the same thing. We call that an isotonic hypovolemia. And they're different. And I'm going to point this out because you'll see this in the literature. Sometimes these distinctions are not made. And that's important to know that there is a difference. And if we talk about other fluid imbalances, we can talk about hyponatremia or hypotonic hypervolemia. And I'm not going to touch on that today. That's obviously an entire other lecture. All right, so let's talk about the one that is most important for our purposes today, and that's hypertonic hypovolemia. You guys know when you sweat, your sweat is hypotonic relative to your plasma. What does that mean? That means the constituents in your plasma are of a less concentration. I'm sorry, I'm going to take it back. The constituents in your sweat are of a less concentration than in your plasma, okay? So typically, if you want to look at sodium, the sodium concentration in your sweat is much lower than what it is in your plasma. And that may be surprising to you guys if you don't know that. You taste your sweat, it tastes salty. You taste somebody else's sweat. I don't know what you guys do. It tastes salty. But it is actually much lower concentration versus what's in your plasma. So as you are sweating and you are losing fluid out of your plasma, the concentration of sodium predominantly begins to increase. And you can see here on the top graph, when we look at plasma osmolality, it increases. You become hyperosmotic. You're taking out fluid, and then the concentration of sodium actually increases as you lose the water. As you're losing the water portion, you become hypovolemic. You lose blood volume. Okay, so that's what we're talking about today. Hyperosmotic hypovolemia brought on by thermoregulatory exercise. And it's also called intracellular dehydration is another term you might see out there. And that tells you that most of the fluid that you're losing is from the intracellular space. This is different than isotonic hypovolemia. What we said would happen if you took a diuretic, or you went to altitude, or you had vomiting or diarrhea. And if we look over here on the left side, you can see this panel. We're looking at plasma volume on the Y and the change in body mass. And we're looking at sweat losses versus furosemide. Furosemide or Lasix is a loop diuretic, so this is going to cause an isotonic loss of fluid. We're doing a study now where we're giving soldiers this to try to mimic that kind of loss, what you'd see if you were sick. And you can see here, if I'm going to ask you, like, what's the big difference that you see between the sweat loss in the dark circles versus the furosemide loss? You see, well, okay, there seems to be a much greater loss of plasma volume using the diuretic versus actually sweating. And that is exactly the case. We look over here on the right side, and another publication out of our lab from Brett Ely. You can see here we're looking at plasma volume on the lower y-axis and plasma osmolality above that. If we look at plasma osmolality, this gives you a really good indication. The gray bar there says the osmolality is 297. That's hyperosmotic. It's increased. If you look on the right side with the diuretic, the osmolality is 292. All right, it's much lower. But if you look below that, you can see in both cases you've lost plasma volume, but you've lost more using the diuretic. And let me make a point here too, because a lot of times this leads to some confusion. Some people in the literature will point out that using plasma osmolality is not an appropriate measure to gauge hydration state. And they'll give examples like this: cold, exposure to cold, being at altitude, diuretic. Okay, under those circumstances, they're right. Plasma osmolality does not work. But understand that when we're talking about exercise sweating, it works very well. All right, let's do a little summary. I like these little summaries, make sure we're all on the same page. So I've already told you that body water is a dynamic state, and I've told you that exercise is going to elicit sweating, and depending on your environment, your intensity, other personal factors, you're going to result in dehydration if you don't match your fluid intake with your fluid losses. And then in the end, when we're talking about loss through exercise, we're going to have a hyperosmotic hypovolemic state versus isotonic hypovolemia with a diuretic. All right, these might be familiar to you guys. Let's take a little look about what happens to some of your physiology when you become dehydrated. And I'm just going to talk specifically about cardiovascular and thermoregulatory responses. So let's take a look at heart rate. Everybody's familiar with that, easy to measure. And you can see here some work from one of my colleagues, Scott Montaigne. We're looking at 4 different levels of body weight loss. You can see 1 through 4%. Looking at exercise over time, 60% of VO2 max. It's kind of a warm environment, 33C. And you can see over time what's happening. Heart rate is going up. And that the other take home here out of this is that the higher levels of body weight loss, the greater levels of dehydration are leading to significantly greater heart rates. So not only is exercise driving heart rate, but you can see that this state of hypovolemia is driving heart rate, and that is going to be graded relative to the degree of hypohydration or dehydration. Okay. On the other panel here, you can see rate of perceived exertion, and it basically tells you the same thing. Heart rate and RPE are very well gauged to one another, and you can see that the higher heart rates in the 3 and 4% body loss are driving a greater perception of work, even though the workload is the same. This, I think, I put this up here and I put the entire reference up here. I think this is a classic paper for those of you who are working in this area from Jose Gonzalez Alonso. And when I was teaching, I was a professor for 12 years, so this is not my first rodeo. I would show this. I could do a whole class just on this slide alone, just on these responses. So, and I've actually changed this a little bit. I took a few things out. But basically, you can tell the whole story, what's going on, just with this one slide. We're looking at an exercise scenario, 20 to 30 minutes of exercise in 2 different environments, what we call in the cold and in a hot environment. So you can see that's represented by the boxes that are open and versus the boxes that are closed. 4% body weight loss, so this is a good level of dehydration. And we're looking at the changes in the bottom stroke volume. So you can see when we're looking at stroke volume changes, when you get to 3 and 4% dehydration, body weight loss, you're seeing a significant decline in stroke volume, particularly in the hot environment. So now we're seeing something else. It depends. It's going to depend on environment, and it's going to depend on the level of dehydration. We've already shown you before in the slide previous that heart rate goes up. Heart rate goes up because stroke volume goes down. Okay, good. So you can see that here, and the heart rate is significantly greater in the hotter environments. It's also greater compared to, you can see here, 0% body weight loss. You can see that cardiac output is maintained to a degree, but it's lower, especially in the heat, especially in the hotter environment at the higher body weight losses. But overall, mean arterial pressure is the same. And why do you think that is? Because if you can't maintain blood pressure, you can't stand up, right? So it's being maintained through these conditions. But when we get to the performance, you can see there's probably going to be a cost. Another slide from Jose, from his work, what I would consider another classic study. Here looking at exercise in the heat, again a 4% body weight loss, relatively moderate, somewhat intense, moderate work, 35C, so it's pretty warm. You can see that cardiac output with dehydration over time is declining. And you can also see that there's a decrease in leg blood flow. So I'm going to show you some of my own work just so I can show that I have a little cred in the area. This is out of a paper I published in Journal of Applied Physiology in 2010. It was a performance study. We did 15 minutes of cycling, and we had them in 4 different environments, 10 through 40C, 4% dehydration. They're exercising at 50% of their VO2 peak. And our work is very reminiscent of what I've already demonstrated with Jose's work. You can see in the 30 and 40C environment, we have a greater change in cardiac output. And you can also see that in that 40C environment of 4% body weight loss, we see mean arterial pressure, blood pressure starting to fall down. And that's fortunate. This is actually a subject in that study. He's on a bike, so he didn't fall down. Here's another it depends kind of scenario. We see here again, this is from my colleague Scott Montaigne, looking here on the above panel stroke volume. But now we're looking at, aside from body weight loss of 3 and 5%, we're also looking at exercise intensity. And what you can see, 25, 45, and 65% of VO2 max, you can see that there's greater changes in stroke volume and greater changes in cardiac output, again, mediated by level of loss, 3 to 5%, and mediated by exercise intensity. So there's another, it depends. Depends on exercise intensity. How about some of the thermoregulatory physiology? This is probably 2 classic papers from my former boss, Mike Saka, and out of Larry Kenny's lab at Penn State. And basically what it shows you is that when you're in a dehydrated state, here if we look on the left side, sweating rate and core temperature, 5% body weight loss, you see a rightward shift in the threshold for sweating to start. So you won't start sweating till you get hotter. And not only that, you actually sweat less. This also goes hand in hand with what Larry Kenny showed. Dehydration, again, 5% body weight loss, rightward shift in forearm blood flow. So less vasodilation, right? Less getting that blood from the core out to the periphery. Here's another similar type graph, again, from my colleagues at USARIEM. Whole body sweat rate on the left, looking at dehydration of 3, 5, and 7%. I don't know if you guys have ever dehydrated yourselves to 7%. It's pretty significant. People tend not to be in a good mood, even at 4%. 7% is very difficult to achieve. What you can see here is there's a graded response in sweat rate in the threshold for sweating. The more dehydrated you are, the further out, or the more heat you have to store, the higher your core temperature has to get till you actually start sweating. And here you see the same thing demonstrated here using esophageal temperatures. I told you about hyperosmotic hypovolemia. So this is just a little slide to show you that those 2 states actually drive some of these physiological changes. So basically what this is telling you is that state of hypovolemia, and in this case we're looking at hyperosmotic state being driven by using a saline infusion. This would be a really cool study. Saline infusion and passive heating. You can use have you guys heard of a perfused suit or perfused shirt? You put a shirt on like you have on now, it's got tubes, and then you put fluid through it. You can change the temperature of the fluid. You can really heat stress people big time doing this. So you can do a situation like they've done here, looking at the esophageal temperature here down on the very bottom on the C panel, and they're driving plasma osmolality by infusing hypertonic saline. I've done some similar things to this myself. It's really cool. So you're driving that response, you're heating them up, and then you're seeing here in the next two graphs a change in that threshold for sweating, and on the top, a change in cutaneous vascular conductance, which is going to be a surrogate measure for skin blood flow. So this is just some of the physiology behind why some of these changes are happening. What's the bottom line? What's the bottom line? The bottom line is you're going to store more heat. You can see here, we're looking at 3, 5, and 7%. This is steady state exercise. And you can see a graded response in core temperature relative to the amount of body weight loss. So there's again, a take home. The response is going to be relative to how much fluid you've lost. All right, so let me tell you what I told you again. Dehydration, as far as cardiovascular and thermoregulatory responses, we have a decrease in stroke volume, showed you that. We have an increase in heart rate, showed you that. Cardiac output tends to go down, more so when you're hotter and more dehydrated. From a thermoregulatory point of view, we've seen an increase in the threshold for sweating, a decrease in sweat rate, a decrease in forearm blood flow or skin blood flow. And the bottom line, what does that result in? Results in an elevated core temperature. And we've already said some of the mediators of that. So what else is playing a role? What are the PENS factors here? Well, we've said degree of dehydration, the environment and exercise intensity. Greater impact with higher body weight losses, higher temperatures, and higher exercise intensities, okay? All right, there's your basketball team. These are some of our soldiers out doing maneuvers. So let's talk a little bit about performance, exercise performance. This is a slide, we've taken this from Adolf. Have you guys, any of you guys in the environmental area heard of Adolf? Man in the Desert. This is a classic work. I've done a presentation on this, on Adolf and Adolf's life. So I actually went to University of Rochester where they have his archive and looked at all of his stuff, from his lab coat to all his notes and handwritten notes from big physiologists. It's really cool. I know it's totally geeky, but it was an awesome time. So if you're really into this area, you can get yourself a copy of this and read it. It's a classic thermal physiology text, and I go back to it quite often, and I've been doing this for like 25 years. So we think that what we've done is actually pretty new. Wow, I'm like the first person to show this. No. A lot of this has been incremental, and Adolf was one of the people who actually looked at a lot of these things in his early experiments. So basically what this slide is showing you is that if you're just going to look theoretically at your ability to do exercise on the y-axis, exercise output as a % of normal, you can see that with the greater body weight loss and the hotter and drier the environment, you're going to have a greater change or a greater diminishment, is I guess how I want to say it, in your ability to perform exercise. This is out of Adolf, and there's a slide of him when he was older. And some of this is based on real data, some of it's estimated using some modeling. And what's really cool about that inset slide there is the guy's actually doing this experiment. So here's the experiment. I meet you in the morning and I give you fluid, all right? I give you either 10 liters, you can see it up here, 10 liters, or I give you 4 liters, or I give you 1 liter, or I don't give you anything. And I say, okay, there's the desert, go march, let's see how far you go. And you can see here, we can look at miles here on the x-axis, 32 miles, and then there's the temperature. And then you can see here on the y, how far did they go? So the white bar, if we look here, 90 degrees Fahrenheit, they have 10 liters of fluid, they go 50 miles. But if you go down here to the very bottom, if they don't have any fluid, they go 20 miles. And you can see as the temperature gets higher, you can see that the amount of work that they're able to do is less and less. Even to here, when we get upwards over 125 degrees Fahrenheit, even if you have 20 or 10 liters of fluid, you're still not able to do that much work. Here's a good slide. I think that gives you a greater breadth of some specific changes. This is actually looking at leg extensions, 4% body weight loss. Leg extensions, you guys know what those are. These are done in a magnet. Okay, so that's pretty unique. This is why I want to show it to you. And what it demonstrates here, and they're plotting this, what people are able to do with leg extensions when they're normally hydrated versus hypohydrated, 4% body weight loss. There's a line of identity, and you can see here on the histogram, there's a significant decrease of 15% in your ability to do leg extensions when you're dehydrated. What about your ability to do exercise? We have here 2 studies, Craig and Cummings and Pecan, both from the early 60s. And we're looking at what we call exercise capacity, your ability to do work. You can see here on the bottom, you have a 1% body weight loss going up to a 2 and 3% body weight loss. And you can see the decrement in work going up to about 20% in your ability to do exercise. Craig and Cummings, above that, also shows a 2 and in this case a 4% body weight loss, and showing an upwards of a 50% decline in your ability to do work. What about aerobic power? You can see that with this increase in body weight loss or increased level of dehydration, there's a decrement in your aerobic power also. This leads to a very interesting question. What do you guys think happens to VO2 max when you're dehydrated? This is a study by Saltine. This is another classic study. He has people in a temperate environment, so it's not particularly hot, 3% body weight loss, 25% workload. So they're exercising. He's looking at blood lactate and looking at oxygen uptake. You can see here, the blue dots are showing you when they're dehydrated, and yellow is when they're well hydrated. The well hydrated folks just go further, but the top bar shows oxygen uptake. Their peak VO2 is exactly the same. His conclusion was what? Dehydration doesn't alter VO2 max, VO2 peak. But if you want to go ahead and look into the literature, if you look over here, if you see the percent body weight loss ranging from 2 to 5%, and change in VO2 max on that panel right next to it. Second to last, you see the Saltine study, no difference. But then if you look at the number of these other studies, there actually are changes in your VO2 peak. But the thing about a lot of these studies is they have different methodologies, different levels of dehydration. They're doing different types of work, cycling versus upright exercise. They have different environments. Okay, so it depends. I'm putting this slide up because a number of us went to the University of Connecticut, and Larry Armstrong was one of our mentors. And so this is one of his slides. I would consider this as a classic study that demonstrates a decline in running velocity with dehydration. The caveat with this slide that has to be kept in mind is that Larry Armstrong used a diuretic. So this is an isotonic hypovolemia. And so what does he show? 1.5K shows a 3% reduction, 5K a 6% reduction, and then if I can see it past, and then probably around a 6 or 7% reduction at 10K. So what we're seeing here, this is a 2% body weight loss, but the decrement in exercise performance is exaggerated as the duration of exercise gets longer. This is from my colleague Sam Trevant. This is looking at cycling exercise, 3% of body weight loss. This is a time trial, so we're comparing the change in performance relative to when they were normally hydrated. And what this really shows, I think, very well is that the decline in performance when you're dehydrated is dependent on environment. So you see here, 2C environment, this is cold, this is probably below freezing. These people are in t-shirts and shorts. Not much of a decrement, about 2 to 3% decrement in performance, 3% dehydrated. If you look up here, 40%, you're seeing almost a 20% decrement. This is definitely showing that environment has a mediating effect on your ability to do work when you're dehydrated. Some of my own work, again, looking at cycling exercise. We have exercise in that bike test that I showed you, 15 minutes of exercise, looking at 10C, 20, 30, and 40C, and their 4% body weight loss. And what are we seeing? Well, in 10C, we don't see a great decline in exercise performance. There's about a 2% decrease in performance. Upwards of about 5% in 20C. About almost a 15% in 30C and a 24% decline in 40C. So there's another good example of environment playing a role. This is a compilation of studies. So what we're trying to do and Dr. Kavoris and I were talking before, is try to take all our work and put it in one place and try to draw conclusions of that. So we've taken 4 studies of my own, John Castellani, who I work with, Sam Trevon, who I work with, put them all together and said, what about skin temperature? Does skin temperature play a role? It's going to be a reflective environment. And what we see here is that these folks are 3 to 4% dehydrated, and on the x-axis, you see their skin temperature. We began to see a decline in performance at around 27 C of your skin temperature. Wonder why that is. Well, you guys are physiologists. Greater skin temperature, greater skin blood flow, right? You have blood going out to your skin to dissipate heat. You have blood going to your muscle to do exercise. You have blood trying to go back to your heart. You need blood to go to your brain. Sounds like a lot of blood and a lot of places for it to go, doesn't it? All right, so this is why skin temperature plays a role. If I can show you no other slide to prove my point that dehydration impacts performance, it's this slide here. This is from a paper that I put together with Sam Trevon, Handbook of Physiology. We looked at every single study, all right, every single study of 2% or greater. And we looked at, you can see in the white bars, these are endurance studies, and the black bars, these are strength studies. We looked at the level of dehydration, and then we said, okay, how many of these studies showed a significant change in performance? Significant, P less than 0.05. Look here, overall, 88% of all the studies showed a decline in performance with dehydration. What about strength and power? Because a lot of times that gets reported as being equivocal, like, maybe, maybe not. Well, what we saw in these studies, so we're looking at, in this case, 43 strength and power studies, 67% of those studies showed a significant decline in performance. All right, so let me summarize again. I already told you that dehydration can change physical work capacity. That's relative to the environment. It's relative to the amount of body weight loss you have, the degree of dehydration. I think it's equivocal right now whether or not dehydration alters VO2 peak. I think that's going to be dependent on a number of different factors. I showed you that performance changes, running velocity changes, cycling performance changes. I've showed you that this also is mediated by skin temperature and the reasons why that's probably playing a role. And then I showed you that literature. So the conclusion here is that what? What would you guys say? At this point in the presentation, if I said, hey, what do you guys think? Dehydration affects performance, yes or no? But it depends. Didn't I tell you that too? All right. When is dehydration important? So this is the take home as to when and why it is important. So I've showed you the literature supports that dehydration impacts cardiovascular physiology, it impacts thermoregulatory physiology, it impacts exercise performance. That's all relative to percent of dehydration, relative to the heat stress, relative to exercise intensity. But I want you to think about something, and I'm not the first person to point this out, is that we are looking at exercise studies that are performed in a laboratory environment. And how many of you exercise in a laboratory environment? None of you, do you? So those of you who are going to do research, some of you are going to do research here, some of you have done research, right? If you're going to do research on something, you probably want to hit it with a hammer to get a response. You're going to spend a lot of time and money doing something, doing an experiment. You'd like to see something happen, right? So we do that. We hit it with a hammer. We do dehydration studies of 3 and 4%. That's the hammer we're hitting. We don't do these studies that we in our lab call 4-minute abs, right? I guess 4-minute abs. It's like 5-minute abs works, but what about 4 minutes? All right, here's my new exercise program. I get 4 minutes. These are like incremental studies. Oh, I gave you 6% carbohydrate solution, and I saw a change in performance. Now I'm going to give you a 5.75% carbohydrate. All right, that's 4-minute abs. So I want you to think about the fact that these dehydration studies are studies that were done where they were hit with a hammer. All right, they use high levels of dehydration, greater than 2%, oftentimes anywhere 3, 4, 5, and 7% dehydration. That's an issue because how many of you actually start exercise in a dehydrated state? Most of you don't. New York City Marathon was just this past weekend. All right, those people did not start that marathon dehydrated. They didn't. So that's something to think about. People start exercise normally, and they progressively dehydrate as the event goes along. So here's something that I published It's in the Nutrition Journal, a paper on hydration and recreational activity, but I wanted to work something interesting in. So we used a model. We have a predictive model that we work with Rich Gonzalez on. We published it. We have 3 different papers that we published this predictive model. It predicts sweat loss for an event, and it takes in other factors. All right, so what we did is we took our model and we said, hey, we got 2 different people. We got somebody who's 60 kg. We got somebody who's 80 kg. We're going to have them run at a moderate pace. So this is, probably most recreational people. So you're doing like a 25-minute 5K, like a 40-minute 10K, 2-hour half marathon, 4.5-hour marathon. You guys got the picture of that kind of runner? Okay. 2 different sizes. And we're looking at 2 different environments, 22C here on the left, 30C on the right. And what you see, we're looking at how much fluid you would lose, the percent loss in body mass. And we have that dotted line that says 2% because we say 2% is about the level where physiology changes enough that it's going to impact performance. And what you see here, the take home, is that people don't even reach 2% in cooler environments, and they're slower, not even up until you get to a larger person at the end of a marathon. You can see the same thing here in a hotter environment. It isn't until the larger person gets out to almost completing the marathon they actually achieve 2% body weight loss. Is this true for higher exercise intensities? Yep. So this is fast. This is like sub 21-minute 5K. This is sub 3-hour marathon. These guys are pretty quick, men and women. And again, you see the same deal. You're not becoming 2% dehydrated in the cooler environment or in the hot environment until you're probably around 18 or 20 miles in. Okay, so you're progressively dehydrated. So when is dehydration important? Well, we've already said lab studies versus lab exercise heat studies are done in the lab. They use hot environments. The temperature was for the New York City Marathon, 50 Fahrenheit. Most mass events are conducted in cooler environments. Lab studies will use things like perfused suits where you can really jack up skin temperature really high. They use high exercise intensities because, again, we want to knock it with a hammer. And here's the other part. They use minimal airflow. When you go outside and you exercise, when you run, you ride a bike, that forward motion creates air velocity, and that air velocity cools your skin. It encourages evaporation. It encourages heat loss. And most of these studies did not have airflow that even was reflective of what happens in the outside environment. Okay, and so there are a number of studies out of Glenn Kenny's lab up in Ottawa that have shown if you have airflow, you reduce or decrease the cardiovascular strain. You take skin temperature down, reduce strain, and performance is not as degraded. All right, so when is dehydration important? It depends. Depends on your initial hydration state. I've showed you that. It depends on the airflow. I've showed you that. Depends on your temperature, depends on humidity, depends on the intensity, depends on the duration. Remember, there are people who do events that last many hours or days. Ultramarathons can go on for numbers of days, okay? But what I also want to say before somebody comes out and says, oh, Kenefick says dehydration doesn't matter now because all these lab studies did all this other stuff. That's not true. That what I've just talked to you about the real world versus the lab does not negate the lab findings. But it just tells you that the lab findings are probably exaggerated compared to what really happens in the real world. Okay, and I think that's a very, very important point. So the effect of whether or not dehydration is significant is going to be dependent on the context of the situation. So when is dehydration important? Well, there are going to be situations where you accumulate water loss faster than you can take it in, or you have a limitation in fluid availability. Hiking the Grand Canyon can be one. They have 2 problems. They have dehydration, they have hyponatremia. People drink too much or they drink too little. It's a long hike. It's an arduous hike. Military conflicts. Second largest logistical problem in the military for any mission is water, delivering water. Yep, it's that big a deal. Emergency relief is another problem. Trying to get water to people who need it after various types of humanitarian crisis. Competitive events like a marathon, an ultra marathon. There are races. I have a friend in April, he's running a 1,000-mile race. It's 1 mile loop 1,000 times. He has 28 days to do it. All right, hydration there is going to be an issue. Okay, and there are more of these events out there than you actually know. There are lots of triathlons. I have friends who do like double, triple, quintuple's 5, right? Quintuple Ironman. I know, it's crazy. Hydration going to matter in that circumstance? Without a doubt. And here's the last thing that I think is important for you to take home. Because I come from New England, and this isn't my statement, it's Mark Twain's. If you don't like the weather in New England, wait a minute. Conditions change rapidly, and oftentimes, at least where I'm from, they're not predictable. The weather people suck. So you might go out thinking, I'm well hydrated. I'm going to go do 20 miles today, and I'm not taking any water with me because it's going to be cool and it's not a big deal. But I can tell you the Boston Marathon a number of times a few years ago thought that, and it turned out to be an 80-degree day. And Chicago had that problem a few years ago, and they had to cancel their marathon because it got too hot. So hydration is important, and even you have to think about starting exercise well hydrated. You have to plan for water availability, to have water so you can maintain your hydration state because you never know what's going to happen. That's all I got. We have time for questions?
Yes, we do have some time for question. Also for the online viewers, if you have a question, you can type it in the lower right part of your screen. So there is a click that you can see, there is a question tab. So you can type your question and we'll try to answer it.
Two questions. One, well, thank you for coming.
Oh, thanks.
My first question is, at your facility, what percentage do you think your studies are using esophageal for body temperature?
Right now, very few. You guys know what esophageal is? To take a probe, it's a piece of wire real thin, put up your nose, goes down your throat, sits about the level of your heart. You guys are all looking at me like I'm crazy. That's how it's done. It's probably one of the true gold standards of measuring core temperature because it's at the level of the atria of your heart where all your blood comes from. We used to do that quite often. Those studies are done very well for like looking at sensitivity for core temperature. We do it less because for the main reason is that we don't have a lot of people who actually can do it. You have to train people to do it. Some people just can't do it. So I would say now, very few. They still get done, but very few do it.
The question is, you work with the Army and a former employee at West Point. I remember it's the Academy. But is there one for the Navy as well as the Air Force?
That's a good question. So we employ people, just in case you guys want to know. We hire folks. We hire some undergrads. We have an ORISE program, the Oak Ridge Institute. This is how we hire individuals. We have postdoc positions sometimes. We have people from all over the country. We just hired a girl from Washington State. She's doing a great job. So there are other we have sister labs, but due to the BRAC of basically realignment and closing, some of those labs have been closed. So as far as the environmental area, we're it. And so we call ourselves Tri-Service. We don't exclusively work for the Army. So the Marines, part of the Navy, they'll contact us. We do collaborate with the Air Force. And the Coast Guard, too, because people forget the Coast Guard is one of the military branches. So we do work with all of those.
And then some of your chambers, do you simulate some of the submarine or aircraft carrier?
Aircraft carrier, not so much submarine. We've taken our hyperbaric chamber and made it. We did the disabled sub study. So like a sub at the bottom of the ocean, and people are in there for like days, and then we slowly increase the CO2 concentration because that's what would happen. And guess what? It's cold and it's wet and stuff. So yeah, we can simulate that. We can make it rain in some of these chambers. We can sort of make it simulate snow. I've seen that. So it's a pretty incredible place to work. Nothing. There's like, how many people here? Nobody has another question.
Any more questions?
So what do you guys think about hydration? Go ahead.
So I know the military trying to have more women involved. With the amount of material women have to carry and their size compared to men, how does that affect like a lot of the hydration in these studies?
It's a good question. So our studies are not exclusive on male volunteers. There are some of the data I've shown you includes female volunteers. I've done a couple load carriage studies. We've taken people and loaded them up 30%, 50% of your body weight on your back. That includes carrying a weapon, which weighs 12 pounds, a helmet, which weighs between 8 and 10 pounds, body armor, depending on how much armor is in it, can be upwards of 20 pounds, and then a backpack filled with stuff. And that is not relative. So that, and those studies are relative to your body size. For scientific reasons, we do that. In the real world, it doesn't matter what size you are. You're going to get a pack that weighs X, and you're going to have to carry it. So obviously, a very small female, a position like, medics have to carry a lot of stuff. They carry liters of fluid with them. They may not be carrying all that stuff just because they may not be physically able to. But the reality is, every soldier is going to be carrying a heavy load, probably a far too heavy load for what they have to do. It doesn't matter if you're a man or woman.
On that note, there's 2 females just passed Ranger School.
Yeah, a third one too. Yeah. So one of the things that we've just done at our institute, Congress asked us to, because now that women are going to come into combat roles, they said, can you guys figure out what do all these jobs entail? What do you actually have to be able to do physically to do this job for anybody, man or woman? So they spent a couple of years doing it, and they're going to go back out into the field to do this. So they actually go and study men and women. They determine the baseline for X task. So here's a task. You got to take a shell, and you got to pick it up. I forget how much it weighs, but I don't know if you guys hunt. This is not like something you go deer hunting with. This is a huge shell, weighs 40 or 50 pounds. You got to haul it up so that it can be put into a tank, so it can be fired. And you have to do that relatively quickly. So if it doesn't matter if you're a man or woman, that's the task. So they went and identified, okay, here's what these tasks involve, and here's the minimum of what you need to be able to do it. And so then, if you're a guy and you can't do it, then you can't do it. If you're a woman who can do it, then you can do it. So that's one of the things that we've been involved with of late.
We have several questions actually that came in from the online viewers. I'm not sure whether we'll have time for all of them, but I will start. In regards to MMA athletes, and it was funny, we were talking about it in the car. Can you make a comment for MMA fighters that they might start already hypohydrated, might start fighting with low body water content, lower than normal?
So the UFC just asked me to talk to their athletes. So I was just in Vegas on Monday to meet with their fighters. I didn't meet Ronda Rousey. I would like to, but I met some other really, really cool people, and that was one of the questions. Because if you're not aware of what goes on in this sport, similar to wrestling, they weigh in, and then they go through about 3 to 4 days of dehydration, usually food and fluid restriction, and that may include exercise. They can lose, we've seen over 13, 15, 20% of their body mass in that many days. Then they'll weigh in, so then they qualify to fight at a particular round in a particular class. And then 24 hours before the fight, they do various protocols to rehydrate themselves back to where they started or even more. So whether or not they're successful in getting back to that pre-weight, depending on what kind of loss they had. Most of them will do it, but the points that I made to these guys and I'll make to you, if you are going to do food and fluid restriction for 3 days, do you think you're just losing water? What else do you think you might be losing? It's possible that you may be losing some muscle mass. Remember, your brain runs on glucose. So does your nervous system. If you have a low blood glucose, where do you think you're going to make glucose out of? Amino acids. They're going to come from your muscle. So we're going to strip some of that away. What about liver and muscle glycogen? Because these guys may be doing exercise. Women too. Think you can deplete your liver and muscle glycogen stores during this? Yeah, you do. So then I've lost some lean mass. I've lost some liver and muscle glycogen. And now I replace all that weight back I rehydrate. They were using IVs, which is now illegal. So when you walk back into the event, while your weight says, yeah, you're rehydrated, but you're still not the same person you were physiologically before you dehydrated, are you? No, you're not. And so what does that possibly mean for performance? think about, do you guys know, this is mixed martial arts. The rounds are 5 minutes long. They typically do 3 5-minute rounds. What kind of activity do you think it is? Aerobic, anaerobic? This is where you guys answer. It is aerobic, but they're also punching and kicking each other as hard as they can. That's anaerobic. This is an intermittent sport, right? It's a mix of both. It's a mix of both. So what I've showed you, you think dehydration is going to affect their performance? Yeah, and the stories they told me when they did walk in, especially with the use of diuretics, this one woman had lost over 20 pounds. She only weighed about 115 to start. And she walked in for her competition, and she was soundly beat very quickly, just knocked out. So yes, it's going to play a role. And the other role too is when they rehydrate, where does this fluid go? Is it equilibrated throughout all the body compartments in 24 hours? It may not be. It may not be.
Thank you. There are several questions. One more interesting question was, what is the hypothesis behind dehydration decrease in exercise performance?
Yeah, that's a good question. There's a lot of different ideas as to why dehydration alters performance. One of the ones that I could propose to you, and it isn't mine because there's a lot of smart people before me, and I've already kind of given you the hint, okay? So when you're exercising, particularly in the heat or just exercising and you're generating heat, I said there's an increase in skin blood flow, right? Because you need to dissipate that heat. And I said, if we look at where all that cardiac output is going, it has to go, name the places. It has to go to your muscle, right? You're exercising. It's got to go to your skin. Your vascular beds, your capillary beds are very, very compliant. You can put a huge amount of blood flow of your cardiac output out into your skin. Right, so now I've got blood to my muscle. I got for exercise to deliver oxygen. I got blood to the skin for thermoregulation. I need to get blood back to my heart for cardiac output. I need to get blood back to my brain, right? So as we continue to, and then if we superimpose hypovolemia on top of that, right? We talk about something called a greater relative hypovolemia. Relative, so if you look at hypovolemia, your central volume. So if I have less central volume because I'm dehydrated, and then I superimpose pushing all the blood out here at the periphery, I have an even greater relative hypovolemia centrally. And that is one of the theories that's proposed as to why dehydration impacts performance. It's cardiovascular thermoregulatory.
I will jump to one of the more recent questions, just because I think it's relative to what you just answered, which is some studies have shown that greater weight loss is associated with better exercise performance. Can you comment on that, please? Throw you the hot potato.
So here's an interesting point to throw out to you guys. So when you express VO2 max, what are the units for that? The relative units for that? mLs per kg per minute. So if you were to lose body mass prior to doing a VO2 max test, for like argument's sake, let's say we just cut off your arm, you'll lose weight, right? So now will my VO2 max go up? On a relative basis, it should, right? Because I weigh less. Yeah. Now I totally forgot your question stuff.
So I have the whole question comes of like losing weight and perform better. So, or could it be that dehydration might even help you to perform better?
Yeah, so we've heard this. So we did a jumping study where we dehydrated people, had them jump, and then put them in a dehydrated state and have them wear back what they did and jump. And we didn't particularly see any decrements. It leads us to believe that there are maybe a neurological component that plays a role here. So I would say that, the body weight loss thing, probably not. Probably not.
Okay. There is another question. You mentioned during your presentation that there is a maximum amount that somebody, whether an athlete or a soldier, should consume during exercise. Can you try to quantify that? Can you say what would be the maximum that somebody could drink?
The maximum amount you can drink. Because, again, it depends, right?
Without being...
Right. There's one rule of thumb. You should match sweat losses with fluid intake. That's pretty much it. Now then the depend part comes is how much you're sweating. And we all have different sweat rates. Some people sweat very profusely. Some people don't sweat a lot. All right, so that if you guys are going to work with people, those of you who work in the field, you're gonna get asked these questions. Somebody's going to say like, well, I'm going to run a marathon. How much should I drink? What are you going to tell them? How are you going to figure that out? They need to figure out what their sweat rate is. That's easy to do. You go out and exercise. You weigh yourself before. You weigh yourself after. You correct for any fluid that you took in or if you peed while on your run. And you can figure out what your sweat rate is for an hour. If they run for an hour, then that's very easy to do. Then you can say, all right, now I know I have an idea what my sweat rate is, and I'm going to try to match that. But understand that in some circumstances, this could be difficult. If you're running very quickly in a marathon and you have a very high sweat rate, Alberto Salazar had this problem, you may have to drink really high levels of fluid, high amounts of fluid. That might be very difficult for you. In my case, here's another example. So before I turned 50, I wanted to qualify for Boston, the Boston Marathon. I've run many marathons, but I'd never run Boston. And you have to qualify. I sweat a lot. I sweat like almost 2.5 liters, probably in that range an hour. That's huge. So that's like I showed you that graph of the histograms, like there are outliers to that. I'm one of those outliers, and there's probably a bunch of you here are also. So what did I figure out? How am I going to go qualify for Boston knowing that I have a really high sweat rate, but in order to qualify, I have to run really fast as I can run. So what else can I change? What else did I change? Yeah, I was prehydrated. Yeah, I would definitely do that. I was peeing for days. Yep. What else could I change? Depends. What are the things it depends on? I can change my environment. I ran the qualifying race in December in Delaware, where there's snow on the ground and the temperature was right around freezing. All right. Do you think that decreased my sweat rate? Yes, it did, because the environment played a role. So I got to sweat less, and my performance was degraded less because I knew I couldn't keep up with drinking at that. So these are the things, like if you're working with people, you have to figure out these things for yourself and for others. If they want to accomplish something, you got to dig into this to figure out what's going to be the optimal thing that you can change. In my case, it was the environment, because I could change that so I could achieve what I wanted. And I qualified, and I ran the marathon, and it got bombed. So there you go.
Okay. Another question. There is a question regarding what kind of fluids we should take during exercise. What would you recommend? And probably I can guess the answer. Depends.
It depends. Fluid is another. You could have somebody talk to you. You could do a whole course on fluids and what fluids to drink. So what do you guys think? So obviously hydration is an issue, so you need to take in something that's for hydration. But if I were to have you drink, a lot of you guys are drinking water, right? When you drink that water, there's nothing in it. It's hypotonic fluid, right? How much do you think of that you hang on to? How much is going to stay in you? How much are you going to pee out? Guess. 100%? You're going to pee it all out? You're going to hang on to all of it? 40%? Okay, good. I respect you taking a guess there. So you're probably going to hang on to maybe half of it, maybe a little more. And the rest of it you're going to pee out. So what are you going to need to do when you take in a fluid to get your body to hang on to it? You have to add something to it. You're going to have to add salt. You're going to have to add an electrolyte. Okay. And so some classic studies that were done by Ron Mon and Sue Sharif showed that when you're replacing fluids, that you would have to drink back, after being dehydrated, 150% of the fluid lost in water in order to retain it, to get back to where you started, as opposed to drinking a fluid that has some electrolyte in it, all right, and that will cause your kidneys. Remember, wherever sodium goes, water follows. So if you have some electrolyte, you can retain that fluid. The other issue in regards to hydration, what else can you put in fluid that's going to be beneficial during exercise? Fuel. And then we can get into a whole debate on what fuel is better and when you need a fuel. And so again, you need to look at what events you're doing. Is it something? Do you really need fuel for a 5K? Do you? Probably not. All right. If you're guzzling Gatorade throughout the entire race because you need the glucose, probably not. So you have to think about the circumstances under which this would be beneficial to know what would be the best thing to drink.
Okay. So, and last one, I know there are like tons of questions and comments that they're coming in. I can barely keep up reading them. So one of the question was, how about in altitude? Is there any special consideration, something that we have to pay more attention if we exercise in altitude?
Altitude is difficult because I already told you, there's two things playing a role there. Not all, but most altitude environments cause diuresis that occurs very rapidly. That's supposed to be a beneficial adaptation for you to exercise at altitude, okay? So that's a good thing, but we know it can impact performance. The other thing, when you're in altitude environments, typically it's what? It's cold too. Not all the time, but a lot of times. So there's another thing driving diuresis. So people are dehydrated, usually initially when they go to altitude. And so a lot of times, I've done a lot of mountaineering, they'll say you need to push fluid. You can't get dehydrated. That's going to cause acute mountain sickness. That's going to be an issue. We need to push fluid, all right? But then on the opposite side of that, becoming somewhat dehydrated is beneficial because it increases your red cell concentration, and that's the adaptation, the acute adaptation to altitude. There's the question. So is hydration important at altitude? Yeah, I would say it definitely is because you're becoming hypovolemic. But in fact, this is another study, and we're probably going to be addressing it fairly soon, is the benefit you gain from being acutely dehydrated at altitude, that altitude diuresis, is that benefit good for your exercise performance, or is that dehydration impact your exercise performance? That's a classic question, and we don't know the answer to that question.
So let's give a round to Dr. Kenefick.
Thank you.